Marvellous. Our webinar is now streaming live on YouTube.
Hello for those early birds who've started to watch just before the start.
And the participants are clicking up. 23, 24, marvellous, 28. Wow, fast.
People were keen to come in. That's always reassuring. It's reassuring as a speaker to know that there's some people there.
People have turned up.
I have a very squeaky chair in my office, so I have to sit still during this talk, which is not like me. I like to pace around normally.
Yeah, me too. Yeah, and actually my chair is, well, it's my wife's chair. This is the glorious confines of my wife's office. And I think we need one of those broadcasting lights on the outside, like live, do not enter.
Yeah. I'm convinced that laptops in the future will have light rings around the edge so that you can light your face while you're doing the video calls. Because I'm sat in front of a window trying to get the light in. That
is a brilliant idea. There will be like,
you heard it here first at the Society for Popular Astronomy. So when Microsoft released them, say it was our idea.
Absolutely. Yeah, it'd be like a makeup mirror in the theatre. Yeah. Wow. So I think we had something like I think we had over 100 people sign up to this.
Ah, great.
Yeah. And the chat is live. So we have already Julian saying good afternoon. So hello, Julian.
Yeah, please do use it. I don't know when I'm sharing my slides if I'll be able to see it, but I will try and check, because if there are questions or comments people want to make throughout, then I'm happy to take them as they come. Mm-hmm. I always worry if people leave it till the end, you'll forget what you wanted to talk about. Mm-hmm. Magnetic fields, yes, in the chat that's just appeared from Julian. They may feature in this talk.
But not dust.
No, I'm definitely not a dust person. Was dust the last talk?
No, it's one of these truisms that have you considered dust and have you considered magnetic fields? And, oh
yeah,
I have a comment and a question.
Yeah, if it's ever anything unusual, then it's always it's the magnetism. That's what
absolutely. Yeah. Well, we're now at 1 minute past 4. I'll give it maybe another sneaky 60 seconds for people to turn up. Oh. So this reminds me of when I was in a telecon with some folk from the States that I didn't know, and it was that kind of silence at the beginning where nothing much is happening, and so I launched in with, "Hello everyone, does anyone know any good songs? Sounds like a great opportunity for a sing-song." And I was expecting, some response, and you could just hear, the dust bowl rolling past as everyone just went, "What?"
When you're sort of semi-anonymous, you can just hide, can't you? You don't have to.
Yeah, I kind of forgot that in the US that there's a different approach to professional environments to the UK. In the UK, it's a little bit more of a joke. But,
yeah, people are much more relaxed. Yeah. Different sense of humour in America as well.
Absolutely.
John's saying the song would have to be "Here Comes the Sun."
Yeah, actually, yes. Yes.
Like the themed chat.
Okay, so it's 2 minutes past 2. So I think we'll kick off. And Hello, good afternoon, everybody, and welcome to the Society for Popular Astronomy. It really is lovely to see everyone here, well, virtually see everyone here. And I do hope everyone is keeping safe and well in this weird situation. And now, obviously, for that reason, we can't be running our meetings face to face at the moment. So we're experimenting with this virtual setup. So please bear with us. I mean, we're not going to get everything right. But we really do want to know what's working for you and I don't know, how can we say, what needs a bit more work. So please do feedback to us on how this is coming along. We're going to be looking at the chat and we're going to be looking at the Q&A during these talks. And we'll be fielding questions from those at the end of each talk. So without further ado, it is my enormous pleasure to introduce Professor Lucie Green, who is Professor of Physics at Mullard Space Science Laboratory, which is the most glorious place to work. It's fantastic. As well as being a TV and radio presenter of many, many things, and as well as being our very own chief stargazer. And the subject of the talk today is solar updates. And with that, take it away, Lucie.
Thank you very much. So yeah, it's great to join you all. I can't see any of you, obviously, but hopefully with the chat we can still interact. Now, I've noticed, I think I've lost the chat from my screen, but I'm sure Stephen can come in if he notices any questions in the chat, just unmute your mic and jump in and let me know. So when Robin contacted me about doing something this afternoon, I was thinking, well, actually, the sun's in quite an interesting phase at the moment. So what I want to do is give an introduction to the sun so that people who are maybe not so familiar with our local star will know the kind of terminology and the structure that I'm going to be talking about, but then go on to why it's in an interesting phase and finish up with a quick look at the Solar Orbiter mission, which is actually what's being shown schematically in my first slide, because we launched this mission just back in February. And then the idea is that because we're all in our homes, maybe people are having more opportunity to go and look at the sun in their back gardens, get out their solar telescopes and so on. So Robin's going to have a look at that aspect of safely observing the sun if people are interested in looking from their back gardens. So I think I've got 45 minutes, so hopefully you're settled in with a cup of tea, sitting comfortably. Let's kick off. So apologies to people who have seen these introductory slides before, but I think it's quite useful just as a way to introduce our sun, because the wavelength of light that you look at the sun in influences what you see. And this is why going into space was such a revolution, because the sun emits across the whole electromagnetic spectrum. So if we're looking here from the ground and we can look in visible light and some radio wavelengths, ultraviolet wavelengths, we don't actually see the full sun. And my introductory slides just show, coming from the visible, first of all, that we're more familiar with. So this is the sun in visible light, looking fairly like a blank disk, but with these dark sunspots on the surface. And it's quite a nice sunspot group on the sort of left-hand side of the sun here. And you can see the dark umbra, the central structure, and then the penumbra, which is more like a sort of flower petal shape all around the umbra. And on the right-hand side of the sun, you might just be able to see some brighter regions, and these are called faculae, and they appear close to the edge of the sun, and you might be able to pick them up in your telescopes. But otherwise, in visible light, there's not a huge amount to see. And I'm slightly biased because I'm a space scientist. If we go then into the ultraviolet part of the spectrum, now we're seeing so much more structure, and we're starting to look at a region of the sun called the chromosphere. So the first layer we looked at, the invisible, was the photosphere. This is the chromosphere. And these images are taken at exactly the same time. So those sunspots that you can see on the left-hand side, they're still visible in this shorter wavelength ultraviolet light. But these bright regions that you saw on the edge of the sun as faculae now appear as a sort of network all over the sun. So there's much more structure. So you see immediately, by going from visible light into ultraviolet and also narrowing down the wavelength range that's being collected, we see just more structure. And this is what I find so exciting as a space scientist, to go on that journey of sort of unveiling the sun. So if we carry on and we go into the extreme ultraviolet part of the spectrum, now we're looking at the corona. And I should probably just mention the temperature of the gases here as well, because that's related to the wavelengths of light that we need to use to see the light coming from those gases. So in the photosphere, the temperature of the gas is around 6,000 Kelvin. And then we've come up in temperature as we've gone down in wavelength. So now as we're coming into the extreme ultraviolet part of the electromagnetic spectrum, we're looking at gases that have a temperature of maybe 1 or 2 million Kelvin. So you can see that very drastic jump in temperature. And what we're seeing now is actually the atmosphere of the sun. And you can tell that very intuitively. It looks like this sort of three-dimensional structure that was sitting on top of the photosphere, and that's because it is. Now, these images come from the Solar Dynamics Observatory, which is a mission launched by NASA. It's been, actually this year we celebrated the 10th anniversary of the Solar Dynamics Observatory just recently. And this spacecraft has transformed our view of the sun. But more than that, the data are accessible. So all of these images are available online. So if you Google Solar Dynamics Observatory, you'll find the website. And later on, I'm going to show you a piece of software that you can download on your computer and use to access these images very readily. So now when we look at the sun, we're seeing its atmosphere, its corona, and you can see how it's structured into these sort of series of loops, bright loops. Especially when you look at the edge of the sun, you'll be able to see them. And you also might notice that the bright loops are collected really in sort of two bands, one below the equator and one above the equator. So there's a lot of structure here that as a space scientist, we want to be able to explain and understand. And then finally, if I go into the X-ray part of the spectrum, now I'm looking at gas that has a temperature of maybe 2, 3, 4 million Kelvin. And it's an image taken at exactly the same time, but now hopefully you can really see these glowing gas loops containing million-degree gas shining brightly. And you can see actually that the brightest ones are over the sunspot regions, or that sunspot group that you could see very clearly in the photosphere. So those images just give us a sort of very quick way of viewing the sun, being a bit like an onion. So from the photosphere with the 6,000 Kelvin gas coming up through the chromosphere with tens of thousands of Kelvin temperature, and then up into the corona where the temperature is a few million Kelvin. And more and different structures coming out as you move through those wavelengths, move through those layers of the atmosphere. But the reason I love to study the sun is because it has character. It is a star that changes on all time scales and all size scales. And one of the challenges we have is to be able to capture that so that we can investigate it, understand it, and explain it, know what physics is happening. So in the talk, as I go along, you'll sort of see different telescopes and different instruments being talked about, because we're pretty greedy and we want to be able to see the sun all the time in all wavelengths of light. We want to look at the big structures, we want to look at the smallest structures, and that's quite a challenge. And that means we have to have this sort of fleet of telescopes to enable us to do that. And I'm going to show you how we're getting on with that progress at the moment. But when we look at the character of the sun, we see some amazing things. So here is, again, an extreme ultraviolet light image of the sun's corona. And you can see now really clearly these glowing arches of gas. And if I run the movie, so hopefully this does appear on your screens, you can see that there are changes. So this is a sped up movie. This probably lasts, I would think, several hours, condensed down into just a few seconds. We're going through different wavelengths of light, but looking at the same region. And you can see that suddenly, apparently out of nowhere, this region, which is sitting above sunspots, suddenly becomes very bright, glows very brightly in these wavelengths of light. And also you see these new loop structures forming. And what you're witnessing here is something called a solar flare. And solar flares are sudden, very energetic events that happen in the atmosphere of the sun. We've known about them since the mid 1800s. And if you have a hydrogen alpha filter on your telescope, then you would be able to pick up these events happening in the solar atmosphere. And hydrogen alpha, to put it in the context of the onion that we were looking at, shows you down in the chromosphere. So you would be able to see the sort of feet of this bright structure in the chromosphere. And then as the flare evolves, you might also be able to see some bright loops forming in the atmosphere too. So this is a solar flare. If we look at a solar flare from the side, so this is an event taking place on the edge of the sun, you can see these lovely loops changing over time. So look at how bright that gas how bright that region of the sun is. That tells me that there's lots of gas there giving off light, making that region brighter over time. But you can also see in the atmosphere around this flare that there are plasma flows, gas flows. You can see now this band going up, gas shooting up into the atmosphere of the sun. And now the flare region that you see, which was very bright with lots of high density gas relative for the sun, is now draining down under gravity. And this sort of speaks to another region why I love studying the sun so much, because it's so beautiful to look at. Aesthetically, I find it absolutely captivating. These kind of events where we see the gas, the plasma, the charged gas raining down, gets called coronal rain, which is very evocative of our terrestrial experience. We always assign the sort of terrestrial terminology to what we see on the sun. So here it's called coronal rain, plasma coming down from the corona. Now it's not rain, it's not in a liquid form, it is in a gas form, but it's dense enough so that gravity is pulling it back down to the surface of the sun. And you can find these movies on the internet, on the Solar Dynamics Observatory website. And then another form of activity, which is actually gives the sun a character that really reaches out into the solar system, are eruptions. So coronal mass ejections. And here we see one lifting off from the sun. So for those of you again who might have a H-alpha telescope, that was a filament / prominence. They are the same kind of structure, we just give them different names depending on where we see them on the sun. And it's a filament eruption, which we also call a coronal mass ejection. When it comes to solar physics, we have many different names for the same phenomenon. So it can be a bit confusing. But this, I would call this a coronal mass ejection, but it would also be referred to as a filament eruption. And you can see, hopefully, as this plasma structure leaves the sun, in its wake is a brightened section of the solar atmosphere lower down. And that is the solar flare. That's the footprints of the solar flare on the sun. And what we know now is that these eruptions and these flares are correlated. When you see an eruption go off, you see a flare happening underneath it, where it originated, where the eruption originated. And the strength of the flare just varies. So sometimes it's very obvious, sometimes it's not quite so obvious as with this one. And then if we follow that character out into the solar system, we can use not only extreme ultraviolet light images of the sun or X-ray images of the sun, and we can combine with it telescopes that take artificial solar eclipses, and we call them coronagraphs. So if I run this movie, it's a composite running over several days. You can see the time in the bottom left-hand side, and you can just see the consequence of that dynamic activity originating in the sun's atmosphere. So the flares, the coronal mass ejections, every sort of white cloud like you can see coming off from the sun, just coming off all the time, bang, 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 they are the coronal mass ejections. And as they propagate out into the solar system, they can be moving fast enough to create shocks ahead of them. And in those shocks, you get particle acceleration, and those particles reach us here on the Earth within about 40 minutes. And here they are hitting our electronic camera. So this is why I say the sun has character. It's dynamic. It's doing things all the time. There's a planet going off to the left-hand side. I don't know what planet that is, but it's so bright it's causing a bleeding effect in our detectors. So this image is actually from 2003. So back when the sun was in a pretty active phase, and we had a series of very large flares, very fast coronal mass ejections, and lots of these accelerated particles coming towards the Earth. And it was the first time actually that I realized how the sun can really have an impact on society, because when these emissions got to the Earth, they interacted with the Earth's magnetic field, and they produced what we would call stormy space weather. So that's another area that I'm interested in. And what we were seeing here on the ground was interruptions to our communication systems. There were some problems with electricity distribution. And I remember airlines grounding their aircraft because of the interruption to communications and the potential risk of what these high energy accelerated particles might do when they come into the Earth's atmosphere. So I remember this event really clearly. It was a sort of a wake-up call for me that what I was looking at, you know, this star that's 150 million kilometers from us, not only is providing us with the energy we need to survive, but can also damage the technology that we rely on in modern society. So there's a lot of work that goes on now looking at forecasting this weather in space, forecasting the solar activity, and mitigating the risks here on Earth. So how can we build resilience against space weather? And that's looked at by government and by a lot of scientists and engineers. So I started off by looking at these different layers of the sun and showing you just now that in the atmosphere we have dynamic activity. But I want now to introduce the link. What is it that sort of ties these levels of the sun's atmosphere together? And if we look back to the photosphere, I showed you an image in visible light, so photons that our eyes can detect. But there's another way we can look at the photosphere, and another way that we can use the light. And encoded in the photons coming from this layer of the sun is information about the state of the magnetic field in that region. So in the chat when we started, somebody raised magnetism. They know me well because this is at the heart of understanding and studying the sun, for me anyway. And one of the techniques I use is to use the fact that the light coming from the photosphere, if it is emitted in a region where there is, say, a strong magnetic field, it will have a certain polarization signature in that light, which then we can pick up when the photons get to Earth, and then we can decode that polarization signal to turn it into a map of the magnetic field of the sun in that layer. And when we do that, we create images like this. So this is, you can see where the sunspots are on the left-hand side of the sun and over towards the right, and where there's some faculae. And if I just sort of switch between, you can see that where the sunspots are, we have strong regions of black and white. And this is a color-coded map in which the north magnetic poles are color-coded as white. So they're regions where the magnetic field is coming out of the sun. So imagine your bar magnet with your north pole, your south pole, and your field lines going in between. So where my field lines are coming out of the north pole, I've color-coded it white. And when they're going in to the south pole, I've color-coded it black. Well, I say I've color-coded it. NASA made these images. I didn't actually create them from scratch. That's quite a complicated process. So if I go backwards and forwards again, you can see the sunspots correspond to regions where we have the strongest magnetic field. but actually there is magnetic field all over the surface of the sun, and it forms a kind of salt and pepper, black and white little, you know, spotted regions. But you may be able to work out that so in this image, I haven't picked a time where there are that many sunspots in this image, but hopefully you can see the sunspots that are there, and indeed the stronger magnetic field regions form two bands, one above the equator, and then kind of, if you use your imagination, there are two regions just below, one on the left and one on the right hand side. But all over the sun is a kind of network and a sort of cellular structure. And that's the pattern that the magnetic field takes on, and I'm going to show why that's the case shortly. But one thing we want to be able to do is understand the three-dimensional magnetic field of the sun, because a magnetic field, you know, takes up space. If you think about the magnetic field of the Earth, you may have sort of seen schematics of the North Magnetic Pole and South Magnetic Pole and field lines coming out. And what we can do is take this sort of measurement of the magnetic field of the sun and create from it the three-dimensional magnetic structure. And when we do that, we visualize it in this kind of way. So we've drawn on the field lines, and you can see them emanating from and going back into black and white regions on the sun. And this is why, when I showed you images of the corona with the gas loop structures, that was why they had a loop structure, because the hot gas in the atmosphere of the sun follows the shapes of these field lines. And that's incredibly important in my talk. So when I'm talking about the sort of photosphere corona link, it's actually a magnetic link, because this magnetism, this magnetic field lines, if you want to visualize them, comes up from the surface into the atmosphere, and it threads through all of those layers that I showed you to start off with. So when we're looking at images and movies of the sun, on the left hand side, I've got my visible light image. I've collected some data over many days, so you can see the sun spinning. It takes about 27 or so days to complete one spin. Nothing really much happens in the photosphere, but then when we look at the movie in the corona over that same time scale, things are changing all the time. It is so dynamic. So I want, to sort of force the point that the images we have on the right hand side are only possible because we go into space. Before the space era, we had no idea that the sun had this kind of character. We had hints and sort of indirect pieces of evidence, but it was only when we launched the first rockets and telescopes that we could see this X-ray glowing gas that had flares and eruptions and so on, and was changing all the time. And I want to sort of show you the benefits of high spatial resolution data. So this is a series of actually ground-based telescopes that are zooming in to see more detail on the surface of the sun. And as we go in and in, you can see this cellular structure revealed. And even, I'm trying to think about the timeline. So Herschel saw this granulation through his telescopes. He made such high quality telescopes that he could see it, and I think he called it corrugation on the surface of the sun. Today we know that these cells are the tops of convection cells, where hot gas in the outer part of the sun is rising, getting to the surface, radiating photons, cooling down, and then moving back into the sun. So these are granulation cells. And one of our quests is to be able to see more and more detail on the surface of the sun. So I wanted to show you this movie, which was released earlier this year, and it was taken by the Daniel K. Inouye Solar Telescope in Hawaii at on the island of Maui. And this is really state-of-the-art technology. So this telescope and the instruments that it carries are just coming online now. So we're just starting to see the first data coming through. And this shows us a series of images of the photosphere. So you can see now, these are the highest resolution images we've had of the sun. And you can see that gas moving. You can see these convection cells sort of turning over. The time on the movie is running on the bottom right-hand side, so you can see how many minutes this covers. And we only see a small part of the surface of the sun because this is such high resolution data. I've tried to put a sort of size scale on it here. So we're looking at a very small region. The full width of the sun is about 109 Earths wide. So this is, you know, a fraction of less than 1% of the width of the sun that we're looking at here. So you can just see this is remarkable detail. And what we're able to do is see how these granulation cells, how the plasma moving actually sweeps little fragments of magnetic field around so that they collect at the edges of these granulation cells. And that's why when you look at the edges of some of the cells, you see these bright features, and that's where magnetic field has been swept together and is influencing how these images look. And it's also why, when I showed you that black and white map of the magnetic field of the surface of the sun, why in the sort of salt and pepper regions, there was this cellular structure. It's because the plasma flow is able to move the magnetic field around. And that's, for me, why the sun actually is so interesting, because the sun doesn't have a static magnetic field. It's dynamic and it changes and it interacts with the plasma of the sun, and it can get moved around and carried by the plasma. So this gives you hopefully a sense that the surface of the sun is always in turmoil. Hot gases moving around and able to carry with it regions of the magnetic field, but only weak magnetic fields. So if I come back then to the sun, I want to show sort of the bigger picture. So here, okay, I've introduced the sunspots, and the Daniel K. Inouye data, telescope data, show us that the sun is changing on small time scales, at small size scales and fast time scales. I want now to take a sort of step back and look at how the sun is changing over many years. And there's a very apparent change that we see when we look at the sunspots on the surface of the sun. How many are there and where are they? So I wanted to show this very important drawing. And it was a drawing made by Walter and Annie Maunder. I think this is in the archives of the Greenwich Observatory, actually. And it shows on the bottom two plots, two traces over time, showing the number of sunspots on the sun. So counting every day, how many sunspots do we see? And you can see that number rises and falls and rises and falls. Now, I don't know how clearly the time scale comes across, but each sort of unit rising and falling is roughly 11 years long. So the sunspot number goes up and down, up and down, up and down. And then on the top, they've got what's come to be called the butterfly diagram. And the story I heard or read about this was that one of the couple would call out the position of a sunspot on the sun, and that's what's being shown here. So we've got time running along the x-axis, but on the y-axis is position on the sun. So north of the equator and south of the equator. And every day somebody read out, on this day there were sunspots at these positions, and the other person plotted the positions. And when they did that over many, many years, so this is probably spanning 10, 20, 30, 40, probably 60 years or so of data here, they saw that sunspots first form at high latitudes, and then as the cycle progresses, they appear at lower and lower latitudes, coming closer and closer to the equator. Then the next solar cycle, sunspots appear at high latitudes again, And as that cycle progresses, they appear closer and closer and closer to the equator. And this pattern repeats again and again and again. So the top plot gets called the butterfly diagram because it looks like a butterfly. And it just shows you as the solar cycle progresses, where sunspots form on the sun changes. So patterns that we want to understand. Why does the sunspot number go up and down? Why do sunspots appear in different places at different parts of the solar cycle? So just to force my point a bit more then about sunspots being regions on the sun where the magnetic field is strong. This movie, it's a bit low resolution, but it shows us 30 years worth of data of the magnetic field in the photosphere. So whereas in this plot, we're looking in visible light, where are the dark sunspots? In this movie that I'll run, it shows us the measured magnetic field. And now my color coding is where it's yellow, I've got my north magnetic pole where field is coming out of the sun. And in blue, I've got my south magnetic pole where field is going into the sun. And the movie is going to start by the sun spinning. So you see the sunspots or the magnetic field regions rotating with the sun. Then the whole sun is going to unpeel itself so that it forms a rectangle. And then time is going to progress. So you'll see over time variations in the magnetic field. So let's run it and see if this makes sense. So here's the sun spinning, loads of sunspots on the sun because we're near solar maximum, 2 bands above and below the equator. Now the sun unpeels itself. This is how it looks if we could see all parts of the sun at once. And now time starts ticking forward. So here we go. So you can see the sunspots diminishing, the magnetic field diminishing. It pretty much disappears and then it comes back, building up to solar maximum, disappearing again, going to solar minimum, coming back again, more sunspots, more magnetic field to solar maximum, and then it dying away again towards solar minimum. And this pattern just ebbs and flows and ebbs and flows. So I think that's just a nice way of just seeing that our sun is a magnetically active star. It's a magnetically variable star. Now, we have these patterns. There are more patterns. So for hundreds of years now, with at least visible light telescopes, we've been looking at what sunspots have been doing. And then more recently, since the early 1900s, we've been able to, from the ground and then later from space, look at the magnetic field of these sunspot regions. And it turns out that from one cycle to the next, there's another pattern that emerges, and it gets called Hale's law. And Hale actually was the person who discovered that sunspots were magnetic features in the first place. And what this law shows is that from one cycle to the next, the magnetic field of my sunspots flips. So actually one thing I haven't said, and I should say explicitly, is that sunspots form in pairs. And one has the North Pole and one has the South Pole. And then you've got your field lines going between. So they're like a sort of analogous to a bar magnet. And when you look at one cycle, so if you look on the left-hand side of the sun, that sunspot group in the north has a black leading colour because my sense of rotation of the sun is from left to right, and it has a white following colour. But if I go to the next cycle, cycle 23, it's flipped. It has white leading, black following. So this kind of rule is really important because it allows us to work out which solar cycle a sunspot pair belongs in. And you'll also notice that the leading polarity, whether it's north or south, not only flips between cycles, but it's also different in opposite hemispheres. So we call this Hale's law. And at the start of a new cycle, the polarities flip. So I hope that's not too confusing. So the solar cycle has an average length of about 11 years. You see this flip-flop of the polarity, the magnetic polarity of the sunspots. And also there's an interesting aspect. So when sunspots start to increase in number, if it's a very sharp increase, you're likely to get a very large sunspot number in that cycle. So I don't know, did it show before? Yes, so in this plot here, you can see each cycle is not of the same size. So some cycles have lots of sunspots and other cycles have lower numbers of sunspots. And that's important, right? Because so think about what I was talking about in 2003 when we had the big flares, big CMEs, big particle events, and it affected us in terms of our space weather. All this activity, the strongest activity comes from sunspot regions. So if we're going to have a sunspot cycle coming up that has loads of sunspots, we can expect lots of stormy space weather. And conversely, if there are fewer sunspots, we might expect maybe less frequent stormy space weather. So having a look at the longer term then, I think I need to speed up because otherwise I'll run out of time. This is a trace of the sunspot numbers going back pretty much to the to our first observations with telescopes. And this really forces the point that some cycles are large and some cycles are smaller. And we have times where actually it looks like a deep minimum occurred. And so what we really want to be able to do is to understand what's coming up for us. What will future cycles be like? We want to understand it from a physical point of view to understand the sun, and we want to be able to forecast it from a practical point of view because we want to know what's coming up for us. And over the last couple of cycles now, our forecasting techniques are being tested. So I wanted to show you the forecasts that were made in the last solar cycle. So at the moment, we're in a minimum between cycle 24 and cycle 25. I want to take us back to the minimum between cycle 23 and cycle 24. Because this was really the first time when people were using models that addressed the evolution of the sun's magnetic field over time, long times, and they made forecasts. So in this plot, you can see the years running from 1995 up to 2015. My sunspot number is plotted on the y-axis. It doesn't really matter what the numbers are, but you can see they rise and fall. And the wiggly trace is the number of sunspots observed. The solid line and the dashed lines show the sort of envelope of that variation and the average, and it's forecasted into the future. So around 2006 or so, or in fact September 2006 is in the plot, people started to forecast, right, what will cycle 24 be like? And bear in mind, we're just coming out of it now, so we can test those predictions. And most people predicted that that cycle would have lots of sunspots, and it would probably be a bit bigger than the previous cycle. But as time went on, the minimum sort of came a bit later than we expected. So in 2007, the forecast was revised. So here we go, prediction in 2006, prediction in 2007. We were still forecasting a fairly large cycle, but just happening a bit later. And then later in 2009, now the plot has been extended. So you see on the right-hand side, it did end at 2015. Now it's ending at 2020, because actually cycle number 24 was quite delayed coming. And in March 2009, I remember being at conferences in 2009, and in the coffee breaks of the conference, people were speculating, oh, well, you know, why is the sun so quiet? This minimum is going on for much longer than we expected. Will there be a sunspot cycle number 24? Or will we go back to one of these grand minimums that we've seen in the past? And it was quite exciting, because when the sun does something different, it's a really good chance to get more data, test models, learn, gain new knowledge. So in 2009, they pushed that forecast forward, that the sunspot cycle number 24 would come a bit later, but also it was going to be a bit smaller. And then we go forward again into 2010. And now we were starting to get the first spots of that new cycle. And I mentioned earlier that those early spots, how the number changes over time, is linked to the size of the cycle. A strong, fast rise to the number of sunspots means a large cycle. But what we were seeing was quite slow. So they downgraded the size of the cycle. And again, so this was in January 2010, things were still quiet, so they downgraded again in February 2011. So look now, the forecast for that upcoming sunspot cycle were much smaller than the previous one. So they'd gone from thinking we were going to have this, fairly decent sized cycle to now thinking, oh, actually the sun is getting quiet. Let's downgrade our predictions. And here we go, the sunspot numbers rising, and indeed we had a fairly small cycle. So so that was a really interesting time to go through, and it shows that our forecasts and our predictions are not yet really capturing what the sun is going to do. So I wanted to show this figure now. So cycle 23 going into cycle 24 was what I just talked about with that the forecast for cycle 24. Now cycle 24 has finished and we're going to go into cycle 25, and again people are making their predictions. So keep this in your mind, because as the years go on now, this is the prediction as of this point in time, that we should be in the minimum phase now. So this prediction has come from NOAA, the National Oceanic and Atmospheric Administration in America, and they oversee this panel that makes solar cycle forecasts. So this was released at the end of last year, but it still stands now. So they're saying this yellow line is the forecast for solar cycle 25. It will be about the same size as the previous one, but remember that's what happened last time and it was wrong. So will that play out? And at the moment, they're saying we are in cycle minimum now, which links with the fact that we see very few spots on the sun. But we will only know if we are in minimum now in several months' time when we look back at the data. So this is my kind of forecast for you, so that in the years ahead, you can look back and think, well, did we actually get this right? And also I wanted to show you this. So this reinforces what I talked about earlier. So the Hale law, where the positive, negative, the north-south flip cycle to cycle. So that means when we're looking at the sun now, we can look at the sunspots, we can look at their magnetic orientation, and we can say, are they in cycle 24 that's just ending, or are they of cycle 25 that we're looking for to start? And this paper by Debyendu Nandi came out recently, and he was looking at that. So these are his results. So here you see that butterfly diagram, because what we're looking at here are positions of sunspots on the sun over time. So we've got latitude on the y-axis, time on the x-axis. And he has color-coded this so that spots or magnetic field regions that are of cycle 25 that we are going into are shown in blue and red. Now he looked at the magnetic field of the sun, and all of his points in red are magnetic features that have the right orientation for cycle 25. A subset of them actually formed sunspots because the field was strong enough, and they're shown in blue. But what I like is that what we can see in this plot is that we are in this really interesting phase where the cycle 24 is ending, cycle 25 is starting, and we're in this overlap. So we're not fully into cycle 25 yet, but it's coming. So the sun is not switching off. And I wanted to say that if you want to compare maybe your observations that you're making with your telescopes to what's happening in space and what the magnetic field of the regions is, you can use this piece of software called JHelioViewer, and you can download it. It's free. There's quite a lot to it. so it takes a bit of getting used to, but maybe if there's enough people in the Society for Popular Astronomy, we could put a workshop online and I could go through how to use this piece of software. But you enter the date, you select an instrument, and then you can see what this spacecraft is doing, because all these images come from the Solar Dynamics Observatory. And that means you can go from images like this to comparing what you see in white light. So actually this is the sun, I think it's last night, because you can get pretty up-to-date data. So this is the latest image of the sun that I could get. This is the corona. There is this sort of bright region that you can see with the gas loops, but when we look in visible light, there are no sunspots there. But when we look in the magnetic field, we see the magnetism, and this is a cycle 25 region. So just to sort of reinforce that point. And this is what Dibyendu Nandi was looking for. Okay, so I think I've talked for quite a long time, but Stephen will jump in if I'm running over or if everyone's left. But maybe just a few final words about Solar Orbiter, because this is the mission of the European Space Agency with strong NASA involvement that we launched in February this year. And it's our mission to go and study the sun. So we have telescopes on the ground, like the Daniel K. Inouye telescope, looking at the sun in great detail. We have the Solar Dynamics Observatory in orbit around the sun, looking across all these wavelengths and measuring the magnetic field. Solar Orbiter is going to go to the sun to get up close. And it will send cameras to look at the sun from the closest we've ever done. So we had a launch in February. Sorry, I'll turn the sound off because that probably doesn't go very well over the speakers. So here we have a launch from Florida on an Atlas V rocket, and I was so lucky to be able to be there and see the launch with colleagues who'd worked on this mission for a long time now. And the launch went absolutely perfectly. It was a clear night, moon was near full, it's absolutely spectacular. Now that video was 25 seconds long, and I chose that length for a reason, because here you see the launch site on the coast at Kennedy Space Center, and we were watching over here at the Banana Creek viewing site, and the distance between the launch site and where we were viewing from meant that the sound took 25 seconds to get to us. So you can work out how far away I was if you know the speed of sound. So we watched this rocket take off, and it looked so graceful because we couldn't hear a thing, and then 25 seconds later the sound hit us, and it was quite remarkable. So we had a late night launch and everything went perfectly. And this is a beautiful shot. This was taken by, I'm not actually sure, I should have credited this, but taken from a different viewing site, and you see the moon up there and Solar Orbiter going on its way. This is nice. This is a video of Solar Orbiter caught by a telescope that's normally looking for asteroids that might hit the Earth. So maybe you can see it just captures Solar Orbiter as it was leaving us. And so I've been working on the Solar Orbiter mission since about 2005. In my department, we built some of the instrumentation on board, so our engineers are involved, loads of scientists all around the world are involved. So it was a huge moment to have Solar Orbiter go and be so successful. This is just a little animation showing the orbit that Solar Orbiter has taken. So we've got the sun here, Venus and Earth, everything else in the solar system stripped out. And Solar Orbiter is making gravitational assists with Venus to get itself into an elliptical orbit around the sun that gets at its closest approach about the same distance that Mercury is from the sun. But also it will tilt itself out of the plane of the ecliptic. So we'll be able to see the poles of the sun for the first time, which is important for understanding what the magnetic field and what the gas is doing up there. So that's just a schematic. You can find all these on the Solar Orbiter website if you Google ESA Solar Orbiter. And then I don't have any images here, but just a few words to say that Solar Orbiter is safely on its way. It is, I think the last time I heard it was about 0.6 of the distance between the sun and the Earth, so 0.6 of an AU, heading closer to the sun. All the instruments now are operational. There are 10 different instruments on board the spacecraft, some measuring and sensing the material around the spacecraft, some looking at the sun. And they have all been turned on, they've all been tested, they've all been gathering data that allows us to commission the instruments. So they're not necessarily collecting science data yet, but it's been, yeah, so far, touch wood, successful. So keep an eye out in the news for Solar Orbiter. There'll be a press release in June, which will show you those first light images. I may or may not have seen any of those. But it all looks really good. So we'll be looking for coronal mass ejections, solar flares. We'll be looking to understand how the solar cycle works. We'll be looking for energetic particles. It's going to allow us to do a huge range of science and be a really important part of our fleet of telescopes. So I will finish there and say thank you for listening, and then maybe Steve will jump back on and I can see if there are any questions.
Thank you, Lucie. Fantastic.
I'm going to stop sharing because then I might be able to see the questions.
Brilliant. We have, and I'll just say
okay, so I can see the questions here.
Yeah.
Yeah, so there's a question. Do we have any new insights into coronal heating out of the PSP mission yet? And how will the Solar Orbiter and PSP help us to understand this phenomenon? Yes, great question. So PSP is the Parker Solar Probe. And I mean, it's quite often the way that America and Europe will have complementary projects, and Parker Solar Probe is America's mission to get close to the sun. In fact, it gets much closer than Solar Orbiter, but it has no ability to look at the sun. It's too close. And so together, they will help us get data about physical processes happening low down in the sun's atmosphere. So coronal heating, as I talked about the fact that the corona has a temperature of several million degrees, 7 million Kelvin. We don't fully understand why that's the way, but we know it's to do with the magnetic field that threads through those layers. And the magnetic field can carry energy and it can release energy. So maybe little solar flares going off all the time, or waves that come up the field. And then because the sun has a hot atmosphere, it sort of, the gas pushes into space, and at some height that hot gas is not able to be held back by the sun, and it actually streams away, forming something called the solar wind. And Parker Solar Probe will get very close to the sun and be in the solar wind, measuring the physical processes that speed up the gases. So Parker Solar Probe will be looking at this hot gas near the sun. Why is it speeding up and streaming away? And Solar Orbiter will be looking at the sun. What's the magnetic field doing? What waves are moving through the field lines? What reconnection? What flares are happening? So the two will work together, and there are definite plans and to put those two spacecraft's data together. So I'm just going to go back to see, make sure I didn't miss anything.
So Lucie, can you hear me?
Enjoyed it. That's always good. So do we have any idea why the solar cycle is the duration that it is? Do you know, this is, I get asked this question, and I don't know. So why is it 11 years long? Why is it not 5 months or 1,000 years? And in fact, there are more cycles than just the 11-year cycle. So when we look at the sunspot number, we've got telescope observations that go back to the early 1600s. But you can use indirect methods and proxies to work out how many sunspots were on the sun further ago than that. And that shows that, yes, you have this 11-year cycle, but then you have other duration cycles superimposed on it. And again, I've forgotten the durations. Maybe it's 100 years is one other cycle, and 1,000 years is another. So there are lots of these cycles playing out. It's not just the 11-year cycle. My not detailed answer is that what's driving the cycle is happening inside the sun, because it's to do with gas flows that evolve the magnetic field. So it will be to do with the specifics of that evolution. But I have to say, I'm not read enough to be able to give you a more satisfactory answer for that. Oh yes, thank you. Someone has told me my sound is down, and it is down because I muted it for the video. So Stephen, if you speak now, can I hear you?
I don't know, can you hear me?
I can, yes, apologies. You were probably talking over me earlier.
No, not at all. I'm just looking at the chat and there's a bunch more questions. So, oh gosh, and they're coming thick and fast. Oh my goodness.
So shall I pick some to answer?
Why not?
Yeah, so there's one about, does the sun emit gamma rays or radio waves? If so, which part of the sun would these come from? Yes, so the sun does emit across all wavelengths. Gamma rays, which are the highest energy waves, come from processes related to solar flares. So you really need a big energy release to generate this radiation. So we see them in some solar flares, certainly not all solar flares, and they tell us about the nuclear processes happening as energy is released, particles are accelerated and moved around the solar atmosphere and collide. And then radio waves. So for example, I'm interested in using radio waves in the atmosphere of the sun that are being generated by electrons spiraling around those magnetic field lines. So the gamma rays I talked about are being emitted low down in the atmosphere, maybe photosphere, chromosphere, and the radio waves come from higher up because they're coming from electrons spiraling around those arched field lines. Oh yeah, what might be happening down deep beneath the photosphere? Yeah, so there's an area of physics called helioseismology that uses the fact the sun rings like a bell and has sound waves bouncing around inside it. And when those sound waves get to the surface, because sound waves are a motion, they make the surface move up and down, up and down. And you can measure those motions and use the physics of that area to go from the motion to then what are the sound waves, and those sound waves carry information about what's happening inside the sun. So we know that the sun is structured on the inside, so it has a core that goes out to about 25% of its radius. Then it has a region we call the radiative zone out to about 0.7 of the sun's radius, where photons are sort of scattering around inside the sun. And then on the last 0.3 of a solar radius is the convective zone, where hot gases are bringing up energy to the surface of the sun. And you saw the tops of those convective cells. But there's still a lot more to be explored. And that's why missions like Solar Orbiter will be so good, because we'll get a different viewpoint of the sun. So we'll be measuring sound waves at the surface from a different viewpoint than we can see from the Earth, and we'll build up a more complete picture. So Solar Orbiter will be important for looking inside the sun.
There were some questions from YouTube. I don't know if we want to pick.
Yeah. So yes, so there's a question, yes, on Earth it is the liquid core, the liquid iron core that generates the magnetic field. What is actually generating the field in the sun? Yes, so that's a good point. And it comes back to, so in the Earth you've got the liquid iron core, which is spinning. I'm massively generalizing, so if anyone's a geophysicist, you might be alarmed at my oversimplification. So you've got a spinning liquid iron core and electric currents. Electric currents generate magnetic fields. Inside the sun, we think there are two different aspects. One is that the sort of original cloud of gas and dust that the sun formed from probably had a magnetic field threaded through it. So magnetism across the universe is a really important area of study. And magnetic fields seem to come about early on. So when that cloud of gas and dust collapsed, it could have brought together the magnetic field that was threaded through it so that it would be going through the center of our sun. So we call that the primordial magnetic field. But then on top of that, because the sun itself is electrically charged. So, okay, in the Earth, you've got molten iron. On the sun, you've got a plasma. The sun is made of a plasma. So you've got electrically charged particles that are moving, and they create a magnetic field too. And the sun, because it is this fluid all the way through with quite complex motions, from that has a complex and evolving magnetic field. So these sunspots that are changing numbers and positions show us the evolving magnetic field of the sun. But there's a lot more to be learned about that, which is kind of reflected in the fact that our predictions for upcoming sunspot cycles are not yet able to capture everything that we see on the sun. So there's still more physics to be put in. So could the sun be considered a variable star? That'd be an interesting question to ask non-solar astronomers as well, because I would say it is, because I see the magnetic field varying. But in terms of the overall light output of the sun across that cycle, it only varies by a fraction of a percent. So the radiative emission is not very variable, but the magnetic field of the sun is. I don't know, Steve, if you've got an opinion on that.
I guess, well, I mean, I'm an extragalactic astronomer, but to me, everything is variable. Really, everything is variable. It's just a question of how much you're prepared to tolerate before you put a little star on it.
Yeah. And the question, was cycle 22 greater or lesser than 23 and 24? I'm going to look back to my slide, actually. I think 22 was a bit greater than 23, because I remember in 2009, when that solar minimum was delayed, and it was a deep solar minimum, that made people start to think, oh, actually, are we going into a sort of quiet phase? Because when we look back, the cycles do seem to be getting smaller cycle by cycle. And it looked almost as if we had a peak in the space age and we were coming out of it. So it was a really interesting time to reflect on how well we actually know the sun. You know, my character of the sun is defined by what I see through spacecraft. In 100 years' time, it might be quite different. So it was a good lesson to learn, that don't take for granted that what we see of the sun now is what it always is like. And a question about, how does DKIS, so the Daniel K. Inouye telescope, fit into the set of instruments around the sun? Yeah, so the Daniel K. Inouye telescope is really about giving us detailed high spatial resolution observations of the surface lower layers of the sun. But also another really important aspect is that it will be able to turn a telescope to the limb of the sun and look at the corona and measure the magnetic field in the corona, which is something that we desperately need. At the moment, all our magnetic field maps are at the surface of the sun, and we make models to understand what's happening above. We have very few observations directly of the magnetic field in the atmosphere, and DKIS will help us with that. And we need that, because we need to constrain our models. And especially given all the eruptions, and for me, all the really interesting activity happens in that magnetic field in the atmosphere. And we want to be able to measure the magnetic field to know what physical processes are driving these activity events. Okay, so it's thought that the combination, it's from John, it's thought that the combination of various cycles is what accounts for the recent for Betelgeuse getting fainter. Is what we might have accounted for the minimum, is that what might have accounted for the Maunder minimum? Do you know, I'm not sure. Various cycles, yes. So that's a really hard one for me to answer. So is it these overlapping cycles that created the Maunder minimum at the end of the 1600s, early 1700s? I think we don't have enough data to answer that. The sun certainly seems to have grand maxima and grand minima, and that comes from using data sets, indirect data sets of solar activity that span long time scales. But the kind of temporal resolution that we have during the Maunder minimum, when we've got sunspot observations, is much higher than those longer term cycles. So I think they might be related, but I couldn't say that research has shown conclusively that that's the case. So do you think the rotation speed of the sun and star would influence its... Yes, so question about the rotation speed of the sun or a star influencing its level of activity. So yes, I think, if I remember correctly, so as stars age, they lose angular momentum and the speed diminishes, of rotation diminishes. And I think that corresponds to a weakening of the magnetic field, which should then correspond to a diminishing in the activity levels. Yeah. Yes, the question, can Jupiter influence solar activity? Yes, so according to Science Focus magazine, the sun vibrates back and forth because of Jupiter's strong gravity on the star. Yeah, I've seen a lot of people talk about that and ask about that. And at the moment, I don't see any research coming out that supports that as being a likely scenario. So at the moment, the thinking is that what's governing the solar activity cycles is all coming from inside our star, and fluid flows inside the star. Oh yeah, as the word corona will have awful connotations for many years to come, can the scientific community come up with another word, perhaps from the word crown in another language? Yeah, it's a hard one, isn't it? So you're right, corona now is the meaning for most people is taken a sad turn. But I don't think, it's hard to change jargon within a community, so I suspect we will still keep using that word. How we might talk about it in public, maybe that would change to be sensitive to the impact it might have on people. Could the sun be a double star? So I don't know of results that would show it is in a binary configuration, but there was some work published some number of years ago that found a sibling star, and they looked at the trajectory of this star and its composition and proposed that it was formed in the vicinity that, or the same cloud of gas and dust that our sun was formed from. And again, this is maybe a question for other astrophysicists, stellar astrophysicists. I think it would be unusual if you just formed one star from the cloud of gas and dust. You know, you look at all the Hubble telescope images of stellar nurseries, and you've got several stars being formed from one overall enormous structure. So I think it might be right to say the sun has siblings. I don't know if that's what you mean by double star, but not in a binary.
Yeah, I'll just say that is exactly right.
So widespread questions. And then the last one is, are there any scientific contributions that amateur solar astronomers can make? Yes, I think so. I think that because it's so important to get the breadth of information and breadth of coverage. So I think bringing together observations people make in maybe hydrogen alpha or calcium-2 filters, especially, you know, some people are taking very high cadence data. Maybe you're filming the sun. So I think those kind of data sets are really valuable, and we would bring it into that sort of bigger picture of ground-based data, space-based data. So to give you an example, the Solar Dynamics Observatory data that I mentioned, those images have a cadence of about 12 seconds. And actually, when that started 10 years ago, that was absolutely amazing. I was used to having one image every 20 minutes, 10 minutes, something like that. So to have 12 seconds was unbelievably fast. And it showed us all these new things. So, you know, what I think is that for people with their own telescopes who might be videoing the sun, what else would I see if I saw a video, you know, playing out, so to have really real-time data would be amazing. So yes, I think there is definite value in bringing together data sets across wavelengths with good cadence as well. Yeah. So thank you, great questions. I'll hand back to Stephen.
All right, brilliant. Thank you very much. And for those questions that we haven't managed to get to, I'm terribly sorry. There's so many things, I'll see if we can arrange for some typed in answers for those who missed out. All right, and thank you again, Lucie. That was absolutely brilliant talk, and I just love the images of the sun. It's just glorious. I mean, we don't know anything as beautiful as that in extragalactic astronomy. Yeah. I'm very jealous.
So I'll stop sharing my video now and hand over to you.
All right, thank you very much, Lucie.
Thank you.
Okay, right. So we've had a glorious talk about the sun, and the next thing we want to talk about is how to observe the sun safely. And Robin, our vice president, has one of our vice presidents has prepared a talk on how we can observe the sun in a safe way. So Robin, are you online?
I'm here, yes. I'm waiting for Dave, our technical wizard, to switch my video on. And then you'll be able to see me on my screen as well. I can't switch it on myself. He's got to do it for me.
You should be able to do it yourself, Robin.
Oh. Well, it says you cannot start your video because the host has stopped it when I try. So
now you're a co-host, and maybe that will work.
Well, what I'm going to do, I'll tell you in sound only while we're waiting for my picture to appear. I've got a few things to show you. One is a short presentation on how to observe the sun, because Lucie has quite rightly said that you can make your own observations of it. And I'll just be showing you a few of the ways that you can actually observe the sun yourself. And having done that, I'll then hand over very briefly to Jeff Elston, our solar section director, who has been putting together a video of the various pictures that our own observers have been showing, and including pictures taken, or drawings in fact taken in the last few days, to show that you can actually observe the sun yourself without too much expense, or you don't need a camera. Ah, here I am. Right, I've appeared. Good. Well done, whoever it was that put me on. And I will now be able to share the screen as well. And having done that, then I will be showing you something very interesting, which is from our member Martin Lewis, who has been observing Venus and will have been seeing Venus up in the sky. It's now virtually over. It's still very low in the sky, but he has been observing surface features on the surface of Venus. Would you believe that it's possible for amateurs to do that? And these are genuine features, so I'll be showing you that as well. So now let me start by sharing my screen, and we'll look at the quick guide to observing the sun. I don't need computer sound for that one. Here we go. Right, this is something that I expect a lot of people know, but it's a matter of how you actually observe the sun. Now, at one time, I would have been saying you should be using solar projection, as you see here. And this is the classic way of observing the sun. And you, as you can see, I know you can't see we've discovered that the computer mouse icon doesn't appear on the screen, but you can see the projection system there being used. And that is the classic system for observing the sun. Then you can, to show you how this is set up, I've got to switch to my slideshow to move this. There we go. That's the way to move the slide on. Yeah. It's important to make sure that if you're going to project the sun, you use, everything is covered, particularly the finder. I discovered this when I noticed that the crosswires in one of my finders were all damaged, and they've just got breaks in. And of course, it's because I'd forgotten to put the filter on the cover on the finder as well as on the main telescope when looking at the sun. So the way to find the sun is to use the shadow of the finder or of the telescope itself to minimize the appearance of the shadow. Then you know that you're looking at the sun, and then you will get the image of the sun coming through the eyepiece. And that is the theory. And then you can project the sun's image onto a piece of card, as we see here. To start with, it will almost certainly be out of focus, but then you can focus it up and increase the size or decrease the size as you wish by moving the card further or closer. Now, that's fair enough. And that was the way that was always been described as the safe way to observe the sun. Now, here on this picture, I'm using a classic Russian TAL-1 telescope, Russian reflecting telescope, that is excellent. It's built like a tank. In fact, there was a story that they converted from making World War II mortars to telescopes at one point, and a lot of them do look a bit weapon-like at times. But the eyepiece in that is made of metal, and no problem with it. But a lot of modern eyepieces are much more are made of plastic, and even, as I say, the cross wires. And here's an example of what can happen if you get heat inside the eyepiece. This was a cheap eyepiece that someone was using, and not me. And you can see that what happened was that the solar image drifted outside the center of the field of view, and it just managed to burn a hole into what's called the field stop. The field stop, you can see there, is the thing that gives you that nice circular defined image outside to the field of view. So the field of view of that telescope was forever spoiled. And worse things can happen. Someone was telling me, I think it was you, Dave, that with Maksutov Newtonian telescopes or Maksutov telescopes, where there is a baffle inside the tube, using projection can actually damage the inside of the tube as well. It puts far too much heat on the inside of the tube, so something to watch out for. And that's the sort of result that you would get if you try to look at the stars through that eyepiece, and that's the way it appears. Fortunately, this is something we don't get these days, but at one time there were sun filters sent out with virtually every small telescope, and the idea was that you screwed them into the eyepiece. The problem with that is that the sun's heat would be focused on the eyepiece and it would crack it. And there's an example of one that actually did crack, and that is potentially a blinder. It could easily blind you, and so never use those filters actually on the eyepiece. However, these days we have a much better system, which is to put a filter over the top end of the telescope, over the aperture. Now, this is one that was designed for a Meade ETX telescope, which is a glass filter, but you don't need to buy an expensive glass filter. You can buy a sheet of what's called Barda solar filter. It's available in A4 sheets. It's around £20 plus postage from a wide number of suppliers, and you make sure that you cut your own filter and make sure that it's well fixed to the top of the telescope and doesn't have any chance of blowing off. Bits of gaffer tape and so on are fine to hold it all in place, but make sure it can't just blow off or get crinkled or whatever. And the great thing about Barda solar filter, it gives quite a neutral view of color. And here's one. That's some photographs, some drawings, I should say, made actually using binoculars to which Barda solar filter had been attached by a guy in the States, Mike Rosalina. And you can see that even using 10 by 50 binoculars equipped with Barda Astro Solar film, he was able to, over a series of days, this was in the States, so he actually managed to get several days where it was clear, and he actually filmed one sunspot and the sunspot group actually rotating across the disk. So you can see that Barda Astro Solar actually works. And here's a rather nice picture I took through a small telescope of a sunspot. That was a few years ago with the sun being occulted by a plane taking off from Heathrow Airport. Another way of observing the sun, and this was something that Jeff Elston will be featuring, is to use the specialized observing H alpha filters. And this is the sort of view that you get there, getting on for the sort of things that Lucie was able to show, just using light of hydrogen alpha. It's right at the edge of the visual observing part of the spectrum in the deep red, but you can see a lot of detail there around the edge of the sun to see the prominences at the edge of the sun. You can see the sunspots don't appear as dense, but there are lots of other features as well. That sort of streak in the middle of the sun is what's called a filament, and that is actually a prominence, the ones that you see at the edge, but seen in silhouette against the sun's disk, and those are quite obvious. Now, we've seen these lovely pictures of the sun in when it was at solar maximum, but even at solar minimum there are still features to be seen. You don't have to take photographs. Actually, taking photographs through one of these small telescopes, the Coronado PSD is one of the popular ones. Here's a picture of one. That is about the cheapest solar telescope that you can buy. I don't know how much they are. They're certainly many hundreds of pounds. You may be able to get second-hand ones, and there are of these there are good and there are bad ones. I've seen some which are really first class and you can see the whole of the sun's disk at once and the prominences, and others where you have to refocus from one side of the sun to the other, and so they are very variable. If you're buying a second-hand one, try and get a look through it first. And that's the sort of view that you can easily get through a PSD. You don't necessarily always get the finest detail, whereas you get pictures taken with some solar telescopes, such as, well, here's another PSD photograph where the guy has obviously got a much more practiced ability to photograph through it. They're not adapted really to taking the lenses out and putting cameras in place. Quite a lot of cameras won't focus on these telescopes. And there's an example of a prominence photographed through one of these Coronado PSTs. The Lunt TS60 THA, I'm not sure if this is the latest version, but this is an updated version of the PSD, and it has a lot more versatility, and those are considerably more expensive as well. Double stacking is a way that a lot of people go. They actually have a refractor and maybe 100 or 120 millimeter refractor, and buy really quite expensive filters to put on the front and at the end and at the back. You need a neutral density filter at the front to stop huge amounts of light getting through, and then you put your filters at the back, and they have double stacked filters so as to narrow the wave band that you're observing from, and that is the sort of image you can get with double stacked filters, with which we're talking about thousands of pounds here to buy this sort of equipment. And there's an example of the sort of thing. So you don't need necessarily to do photography. That's a picture drawn by Ian Lee back in 2011, showing sunspots and prominences and so on. And in a minute, I'll be able to show you a picture taken by Ian, or rather drawn by Ian in the last few days. And as you will be able to see, there's still detail to be seen on the sun. So that's the end of that presentation. Now let me share my screen with the interviews I did with Jeff Elston the other day. Just hold hard while I get that up. I'm not sure if I've shared the video as well. Hold on. Share screen, share computer sound. That's what I need to do. Windows Media Player, share. Right, there you can see it, and it started quickly, so I'll start it again. Right, hope you can all see this.
Well, I started off with this picture of a huge sunspot that was seen in 2014. Obviously, we don't see sunspots like this at the present time because we're around solar minimum. So what we get is very small and insignificant. But this shows a typical structure of the sunspot. It shows the sun's surface and the granulation, and then you've got the darker central areas, the umbra, surrounded by the lighter penumbra. And there's also a couple of light bridges in there on the main sunspot. That's where the photosphere is breaking through. This was taken by Mick Jenkins, SPA Solar Section member, and he's very helpfully put a graphic of the Earth for comparison on size, so that it dwarfs the Earth. The next one, this is also taken by Mick Jenkins, of a prominence on the limb of the Sun, the edge of the Sun. The black disk is added afterwards, but it does help to sort of show up the structure of the prominence as it arches out from the edge of the Sun. This is very cool, dense plasma gas, sort of squeezed between the magnetic lines of the Sun as they come out from the globe of the Sun. This was taken in 2015. This one was taken by section member Carl Byron. He's using a fairly biggish telescope and a Daystar quark attachment. It's a monochrome image, but it's got a tremendous structure. It almost looks like cirrus cloud. It's really stunning. The next one is also from Carl Byron. It shows a plage. This is what the Sun looks like in hydrogen alpha light. What you've got here is you've got the chromospheric network, which is like the spiky sort of structure all around it, and in the middle you've got the sort of the whitish blotches, and that's the actual plage. They're very closely associated with faculae, which you see in white light. They're not exactly the same thing, but they're very closely related. And the next one is in colour, also from Carl Byron. This shows a minor flare. That's the bright area. The dark blotches is the sunspot. You can just make out the penumbra around the edge of it, and the chromospheric network, and then the bright area is the flare. I've been lucky enough to see not this flare, but one like it visually with the hydrogen alpha telescope, and it's really quite exciting to see the sudden brightening of a region on the Sun, and then over a period of about 20 minutes, it's gradually brightens and then fades away and changes shape and everything. It's really quite exciting. The last two, these are actual drawings taken quite recently, a couple of weeks ago. These are made by section member Ian Lee, who's using a Coronado PST visual telescope, hydrogen alpha telescope. Sorry about that. And you can see the prominence is drawn on the edge of the disk. No sunspots, but there are some plage drawn in yellow, and the little black squiggle is a filament, a section of filament. A filament is a prominence seen against the disk of the Sun. It shows up as dark. And if I can just about go to the next one, you can see this is 2 days later. And if I switch back and forth, you can see the rotation of the Sun carrying the prominence across, and filament as well. So although we've got a lot of people imaging, we've also got some that are making drawings still. So it's good to sort of see that. But that's how it was when I first started. You have to draw everything that you saw. But the images are really spectacular.
So the message is that if you want to see features on the Sun at the moment, you really need one of these H-alpha scopes, don't you?
You do really, yes. I mean, it pains me to sort of say it, but yes, there's not much to look at in white light at the moment. It will change as we head into the new solar cycle. But to really sort of see anything at the moment, you do need hydrogen alpha.
But the good news is that the new cycle has actually started. Is that right?
Yes, that's right. Minimum was expected to be around about April 2020. I would say that we are certainly at minimum we are seeing some cycle 24 sunspots and occasionally some cycle 25 sunspots. The way that you know that they are different is that you look at their position on the sun, their latitude. The cycle 24 sunspots are fairly low latitude. That is about sort of 5 degrees above or below the solar equator. And the cycle 25 sunspots will be much higher up at around about latitude 30 north or south of the equator. And that's how you kind of can tell which ones you're looking at.
Well, the prominence that's on the screen now is actually quite impressive, really, isn't it? Quite often the ones that you get even at solar maximum aren't any bigger than that. So there is quite a lot of activity going on.
Yeah, that's right. Actually, yesterday the day before, I was lucky enough to get out with the hydrogen alpha scope, and there was a very nice prominence on the north limb of the sun, and it's a bit like this one, a bit like an arch. Very nice to see. So even at the moment when the sun's fairly quiet, there's still plenty to see in hydrogen alpha. It's not always that way. Some days are blank, but there's more to see than there are in the way of sunspots.
One thing about prominence is that they do move, but they move much more slowly than people might imagine, having seen time-lapse videos which show them leaping off the sun and falling back again. Those are very much speeded up, aren't they?
They are, yes. They're taken over several minutes or even hours. You do sometimes get active prominences that will move fairly quickly over minutes and change a lot in that time. But that's the exception, really, and you only really see those around about sort of solar maximum.
Right, so be patient, and now's the time to get your eye in, looking for these prominences, and it can only get better. I suppose that's the answer, isn't it? Yeah.
Yeah, it is. Yeah.
Good. Okay. Well, thanks very much, Jeff, for running down the latest on the sunspots, and we hope that people will get out there and start observing. And as you've shown with this picture here, you don't actually need to get into all the webcam imaging. You can use them visually. This was taken with the Coronado PST, was it, or another?
That's right. Yeah. Yeah, Coronado PST.
Which is one of the cheapest H-alpha telescopes you can get, isn't it?
It is. There is another contender on the market at the moment, which is the Quark Solar Scope, I think it's called, Solar Scout. And that can be bought for about £600 to £700.
So it's okay. It's a bit of an outlay, but comparable to the cost of a decent webcam for deep sky imaging. So and you don't need to lose much sleep observing either. So that's the advantage of solar work. And at the moment, presumably we've got plenty of, well, at the moment outside it's lovely and clear and plenty of good views of the sun. So get out there and observe.
Yeah, ideally what you need is a fairly good deep blue sky with no high thin cloud. But yeah, a day like today is almost perfect, really.
Super. Okay, well, thanks very much, Jeff, for giving us the latest from the solar section, and we hope this encourages a few people to get out there and start observing. Hi, right, back again. Oh, I've got to stop his video running. It's on a loop. Hold on, don't panic. You won't believe this. I can't find this on my desktop to stop it.
Is it definitely still running? Because I can't see it.
You can't see it. I can just hear it. Okay, well that's fine. What I'm going to do now anyway is to share you another video. Oh, there's my Windows Media Player. I've found it now. So it was playing and I could hear it in my ear. Right, okay. What I'd like to do now is to show you what I trailed earlier on, pictures of Venus. Now, we've been seeing Venus in the sky beautifully. It's still there. The last gasp of it really is up in the sky as a very thin crescent. But Martin Lewis has been observing recently, and he has been able to actually record, as I say, surface details on Venus. So let me now play this video, which is another. Hold on. I've got to share sound as well. Share screen. Bear with me while it starts to play. I can't stop it playing and then without sharing the sound as well. Hold on. Yeah, you should be able to hear it.
Today's webinar. Wanted to talk a little about what I've been doing in the last few weeks with Venus. It's been a great apparition for Venus, the 2020 evening apparition. Venus runs through 5 evening apparitions in 8 years, and the 2020 apparition is the best one of those 5. So Venus is high up in the west in the evening sky, and probably most of the people, most astronomers and even non-astronomers have noticed it very bright in the western sky as the skies darken. So I've been doing my normal infrared and Venus imaging, and here are some infrared images taken on different days through April as the Venus approaches the Earth and the phase narrows. I've been using a smaller scope and also my fossil light 444mm Dobsonian telescope on an equatorial platform. So this is a home-built telescope, f4.4. And that's I don't have an observatory, so I moved to different places in the garden to allow me to reach different parts of the sky.
Just been told that you can't see the video. Hold on, I'm sharing the wrong screen. I will try this again. Stop share. Let me just pause that and then I can share it properly. This is annoying. I can't find the window on my screen to share with you. Ah, found it. Share computer sound. Right, let's try it now.
Listening on the SPA webinar. Wanted to talk a little about what I've been doing in the last few weeks with Venus. It's been a great apparition for Venus, the 2020 evening apparition. Venus runs through 5 evening apparitions in 8 years, and the 2020 apparition is the best one of those 5. So Venus is high up in the west in the evening sky, and probably most of the people, most astronomers and even non-astronomers have noticed it very bright in the western sky as the skies darken. So I've been doing my normal infrared and Venus imaging, and here are some infrared images taken on different days through April as the Venus approaches the Earth and the phase narrows. I've been using a smaller scope and also my fossil light 444mm Dobsonian telescope on an equatorial platform. So this is a home-built telescope, f4.4. And that's I don't have an observatory, so I moved to different places in the garden to allow me to reach different parts of the sky. This is one from just a few days ago, showing how thin Venus is now. Inferior conjunction is on the 3rd of June, so not long away. So it's getting very thin now and pretty big. So I've also been imaging with an ultraviolet filter, and that allows you to see cloud detail on the surface of the planet. And here's one from the 24th of April showing some quite fine detail in Venus's atmosphere. But this year I've been doing something quite different. It's an excellent apparition, and I've taken the opportunity to have a go at imaging Venus with a 1000 nanometer filter. So this is an Edmonds filter with a 25 nanometer bandwidth. And when you do that and look at Venus in those wavelengths, the atmosphere is essentially transparent, and it allows you to see thermal radiation from the actual surface of Venus on the night side. It's drowned out on the day side, but if you look at the night side, you can see those thermal emissions. And you can see cooler regions which are higher, which appear darker. So this is what it looks like with that filter. There's my preview screen on the left-hand side. I'm using long exposures. I'm using a 200 millisecond exposure, which is about 10 to 20 times longer than I'd use on most planets. And I'm using the camera at prime focus to maximize the image brightness, because this is all about seeing something that's very faint against quite a bright background, the darkening evening sky. Is noise, really. So I want to show you now a video of what it would look like on screen. So let me just show you this. So hopefully there you can see a video and you can see the night side. So this has been boosted in gain in gamma to show you the night side there, just as I would be able to see it during the recording. Only 4 frames per second there. You can see the diffraction spikes. It's a Newtonian, so you get these diffraction effects from the secondary veins, which show up as these bright crosses. And very fortunately for me, the orientation of Venus matched exactly the orientation of the veins. Perfect, so it's perfectly positioned, and that is just what you get. I was very fortunate that I didn't have a diffraction vein going right through the middle of the crescent. So going back to the presentation. Okay. So if you take 30 or 40 minutes of video and combine them, you end up with an image like that. So hopefully you can see these darker areas on there, which do look a bit like noise variation, but they are real features. And these are features that are seen on Venus at inferior conjunction in those wavelengths, and the same features repeat at each inferior conjunction. There's some sort of pattern that Venus repeats on an 8-year cycle with its apparitions, but also there's some lock between the rotation, the year, the day, and the Earth's year, so that we always see the same face of Venus at inferior conjunction. Here's one which has had 72 minutes of accumulated data. So you've got a smoother image there. And again, you can see these same features there coming across. And what you can do in a program called WinJupos is to unwrap the planet and make a map. So project it onto a rectangular latitude and longitude map. And these are the features from the globe that you just saw, the normal view that's been unwrapped. And if you overlay that against the Magellan altimetry data, which is the height data, you can see you've got a match for these areas, this H-shaped region that you can see here. Phoebe Reggio corresponds to this similar shaped feature here. Above it, you've got Beta Reggio, 2 higher spots there, and a double dark feature here, and Asteria Reggio here. In the morning apparition that is coming up, you'll see this feature. So this is a very distinctive feature that will be seen in the morning for anyone who wants to try 1,000 nanometer imaging in the next few months, the other side of inferior conjunction. So I've managed to extend my viewing window slightly by perching my telescope on some concrete blocks. Fortunately, wicks opened at exactly the right time to enable me to buy some concrete blocks and elevate the telescope to look over the neighbours and be able to get a last view of Venus before it disappears. And with that, I've managed to create, use that data to create a GIF animation there running from the 2nd of May to the 19th of May. And hopefully you can see these darker patches migrating across the surface as the planet rotates. So they are very subtle and they're almost lost in the noise, but the fact that they rotate with the planet and they correspond to known features says that they are real surface features, and you really are looking at the surface of Venus there, which you know, it's been quite extraordinary to do that. So hopefully that'll be of interest to the listeners, Robin.
Yep. One question is, how much does that filter cost?
It is about £270. I was very fortunate that I applied for a grant to the BAA, and they were very kind enough to give me a grant to cover the cost of the filter and a camera, a specialist camera for planetary imaging. And without that, none of this would have been possible. That was the main barrier to me doing the work, was the high cost of the filter.
And what is the camera you're using?
So I've been using a Point Grey, now Finger Lakes manufactured Chameleon 3 camera, but a lot of these have also been taken with an ASI 174 camera, which has got large pixels and obviously gathers more light and is beneficial as far as reducing noise. So I've been using, I started off using both cameras, and the latter part of the apparition I've just been using the ASI 174 camera.
Now, going back to the question of the ashen light, do you think there's any chance that people would have seen this visually?
It's very difficult to see on the screen unless you boost the contrast and boost the gamma. You can just about see it if the conditions are exactly right, but then you're viewing at 1,000 nanometers. So unless anyone can see in the infrared, I think it's very unlikely that they're seeing this phenomenon, although, you know, people have discussed other things that may possibly give light emission in normal visual bandwidth.
If there were volcanoes erupting, for example.
Yes, say a chemical change in the atmosphere that leaded to some sort of phosphorescence or something, or aurora. So I'm not dismissing it entirely, but I don't think this 1,000 nanometer emission is the explanation for the ashen light, although there may be other things.
So the mystery continues. Well, I think those are super photographs, and it's amazing that we can now image surface details on Venus, whereas not too long ago it was necessary to send a radar probe to Venus to see the effectively the same details, although not so. That was in much greater detail, but then the difference in cost is enormous as well. And so NASA could have observed from St Albans and got the same results. Good, that's great. Thanks very much indeed, Martin.
Okay, thank you very much, Robin.
Right, I'm going to stop that again. I can hear it still in my ear. Let me just stop the player. Right, okay. The last thing I've got for you is to look at some of the things which have been seen, which we're likely to see in the sky in the next few weeks. And this is where I've got to start another PowerPoint. So let me just do that for you. What's up? Usually I do this at the at each meeting. I show you the sky that's appearing in the, that's going to be coming up. Can you see that? I hope so. Okay, right. Well, I will assume on the basis that that you can all see that. What's up for May and June? Right. This is the view that you would see tomorrow night at about 9:30 or so. And this is the view from a software called SkyMap, which is shows stars right down to the horizon. It's not as good as Stellarium in terms of giving a realistic view, but Stellarium does have a problem with the crescent moon, and SkyMap shows it very about the right sort of size. So we will see the crescent moon, we will see Mercury, and we'll see Venus in the sky together. Now you have to look for only a short time after twilight in order to be able to see this, but nevertheless that will be a wonderful sight for photography. Mercury is quite faint. People were saying you'll be able to see it with the naked eye. Yes, you can, but it's not really as bright as you would like. So Mercury there is probably best found between Venus and the moon tomorrow night. Also on this image, you can see a couple of comets. Now, they won't be visible at 9:30. There's the much lamented Atlas, which was hopefully going to be a very spectacular object. I've left on here the magnitudes. I don't know if you can see it, that the magnitude of Atlas was meant to be something like 0.6 at the best predictions, but it never turned out to be. And similarly, Comet Swan was meant to be magnitude something like 0.1, but both of them have let us down rather badly. Comet Atlas, of course, Y4, it broke up almost completely, and I don't think it is now an X-comet. Swan itself has been a dying swan and has not been anything like as bright as we had hoped. It had an outburst which made everyone believe that by now it would be quite spectacular, but this is the best sort of view that we got. This is one by Paul Sutherland a couple of nights ago. On the 20th, and that was in the early morning time, and there it is, very difficult to see and certainly not visible with the naked eye, not even with binoculars, I think. What's happened to it is this. You can see there that the comet was pardon me, brightening quite well, and then it had an outburst up to about magnitude 5 or even brighter, and this was when it was in the southern hemisphere, and it showed a beautiful tail, and people thought that it was going to be really spectacular if it continued that upward trend up to about magnitude 1 or so. But in fact it actually faded, and you can see there that the comet has now faded quite considerably from what it was meant to be, and it hasn't even got to perihelion, which is this line here. So I'm afraid Comet Swan, we've had the swan song from Comet Swan, and although it is in the sky, it is hardly visible at all. However, there is Comet Pan-STARRS, Comet 27T2, which has been up in the sky for some considerable time, and that is also much more easily visible, although a much fainter comet. And you can see it's up in the top of the view there, picture taken by Stuart Atkinson against M81 and M82. So that will be visible over the next few nights, and well worth a look if you've got suitable imaging and perhaps with binoculars as well. And I just wanted to bring you forward to July, we're hoping to hold our next meeting sometime in July. This is for actually July the 25th, when I hope we will be holding our next meeting. This shows the sky. You can see up in the top right here, the constellation of the Plough, or the feature of the Plough. And here's the track of comet Neowise, which should be quite a reasonable object, about magnitude 6 perhaps, during that time. And there is comet Lemon, which will also be not too bad at all. And there is a comet T2 Pan-STARRS visible also in July. So maybe in a couple of months' time, we will have some comets to look at. And they're not likely to be as spectacular as we had hoped, but nevertheless, there will be hopefully something to look at. And to keep an eye on those, go to the SPA website, popastro.com, and we will tell you the latest from those. So hopefully you have now been brought up to date with what's on the sky. And I will now hand back over to Stephen to close the meeting. And thank you very much, and sorry for all the glitches.
Thank you very much, Robin. That was absolutely fantastic. There was so much information there, and it's really good to know how people can get involved in so many ways in astronomy. And I particularly liked the Venus images and that glorious piece of software that you can use to map your imaging to existing mapping. That's fabulous, actually. And yeah, I'm really glad that exists. So thank you, everybody, for tuning in. If you have any questions, I should start my video, by the way. If you have any questions or comments about how this Zoom session has worked, then please get in touch with us by email, or however, one of the many ways of messaging us on Facebook or on Twitter, or however else. We'd really like to know how this is working for you, and we'd really like to hold more of these in future. So help us make this better. So thank you very much, everybody, for tuning in, and stay safe, and we'll see you again soon.
And thanks also to Dave Eagle for doing the technical side.
Hear, hear. Thank you very much, Dave. All right, take care, everyone. Bye-bye.
Bye.